this short clip as we continue waiting for the other students.
Thank you, Molly.
Never try to attempt an experiment without an adult supervision. We often read in textbooks that light travels in a straight line. Do you believe that? Have you ever observed the beam of light entering inside a dark room through a tiny hole in the window? What do you see? Do you see light traveling in a straight line? Hello friends. Today we will perform an experiment to prove that light indeed travels in a straight line. All that you would need to start the experiment are 3 old CDs. So the CD should be old because during the experiment they might get scratched. Thread, a candle, and 6 clips. These clips we normally use to dry clothes. So first of all, we will have to make a stand for these CDs. So for that, we will make use of these clips. So hold the CD upright and then fix the clip. Please make sure that the CD remains upright, that is, it should be perpendicular to the plane of the table. So this is ready. In a similar way, we will do it for the other 2 CDs. So now all the 3 CD stands are ready. So what we want to do now is, we want to align these 3 in a straight line. We have to align them in such a way that the holes of the 3 CDs lie in a straight line. So how do we ensure that they are in a straight line? So for that purpose, we will use a thread. So we take this thread and we tie it straight on the table. So you can make use of sellotape to fix it at both ends. So you see, now you have a straight line. So now we'll place the CDs one after another. So now when you place them on the thread, then you know that they are exactly in straight line. Now you take the candle and place it at one end. You can place the candle also on the thread. So now make sure that the tip of the candle and the holes of the CDs, all of these lie in a straight line. So for that, you will have to ensure that the height of the candle and the height of the hole of each of the CDs, they are the same. Now try to observe the flame of the candle from the other side. So your line of sight should be same as this line, the holes on the CDs. And you are able to see the flame right now. Yes? Okay. Now, why do you see this flame? That's because light travels through these holes and reaches your eye. Now let's see what happens if we displace the middle CD slightly. The moment we displace it a bit, what happens? Are you still able to see the flame? No. Why did that happen? That's because the light came here and it got blocked here. Because we have displaced the CD, the hole is not there. So the light is not able to come any further and you are not able to see it. Now, have the ability to take curved turns. In that case, light could have actually taken this turn and then it could have come through this hole and you could have seen it. But since light travels in a straight line, therefore we did not see the flame. So this experiment very clearly proves that light always travels in a straight line. Few important points to be noted while performing this experiment. CDs must be perpendicular to the plane of the table. All CDs should be used. Holes of CDs and candle flame should be in a straight line. Presence of the thread ensures that the CDs lie in a straight line. Line of
Okay, I believe, do we have the quorum now for the students? Do we have all of them now?
Yes, Mr. Sifuna.
Okay. Hello, this is Mr. Sifuna. Today we want to learn something about light. And in the first place, we have to know, you should be able to explain to somebody what you understand by light. You cannot just say that light is anything you are seeing. We can't see light. Light enables us to see. So we should first of all start by knowing what is light. This is a form of energy that enables the human beings and animals to see. And it enables plants to manufacture their food. So for this topic, which is talking about direct linear propagation of light and reflection at plane surfaces. So look at the topic, the title itself, understand it first, rectilinear. Rect is something which is straight. Linear means something to do with a line. Propagation means transformation. And then, of course, light, a form of energy. And then when you talk about reflection, here we are going to talk about bouncing back of light. And then when you talk about a plane surface, this we are referring to a surface which is straight. It's not curved, that's a plane surface. So when you talk of rectilinear propagation of light, we are talking about the straight transformation of light. So the key objectives that we are supposed to have for this topic, when it comes to KCSE, for example, and you are supposed to revise for it, or any exam, we must first of all understand what rectilinear propagation of light is. The experimental treatment, the video you have just seen, we are supposed to know it. We should be able to describe the formation of shadows and eclipses. We should be able to state the laws of reflection. And we must be able to verify experimentally the laws of reflection. So all these that we are seeing here, that's the objectives, that's the syllabus, what we are supposed to know. But I want us to go straight to the topic itself and start the key areas. So I'll share you a slide where we shall start from. So in the first place, we are supposed to understand the significance of light. I've already told you it enables human beings and animals to see, because animals have eyes, human beings have eyes, so they should be able to see. So it's a form of energy. So if you are asked by somebody, what's light? Don't struggle to talk about light. Don't say anything that enables us to see. It's a form of energy. It will enable you to see and also animals to see. Now, we have various terms which are related to light. I think we can move on to, before we look at the terms related to light, sources of light. What are some of the sources of light? Omar Soyan, can you try to tell us any of the sources of light? Omar Soyan? Name any source of light that you know.
Sun.
The sun, very good. Rueda, name for us another source of light. Yeah, I want you to answer that question, Rueda. Any other source of light that you know?
Lamp.
The lamp, very good. Abdikarim Ahmed.
Candles.
Candles, very good. Abdul Basid.
Electric
Sources
light.
of light. Name for us any source of light.
Electric light bulbs.
Electric, fires and lamps, that's very good. There are so many sources of light. So among those sources of light, we have those that produce their own light, and we have others that do not produce their own light. So those sources that produce their own light, they are known as luminous objects. They produce their own light. We can also refer to them as incandescent sources. They produce their own light. And those ones that do not produce their own light, we refer to them as non-luminous. So we have those two main sources of light. We have luminous objects and non-luminous objects. So luminous objects produce their own light. Non-luminous objects do not produce their own light. So I want us, in our everyday experience, in everyday life, let's name some of those sources that produce their own light. Hassan Ahmed, name for us any source that you know that produce its own light. Hassan Ahmed, please try. Okay, Salma Ali. Okay, I like us to make this, you know, physics, we have to interact, we have to talk, we have to give answers. That's how we shall learn the physics. Otherwise, if I'll talk from the start up to the end, you may not remember anything. So I'm requesting that you just raise up your hand if you are ready to answer any question. Let's interact, let's talk. That's how we shall make physics a very wonderful subject, and that's how you love it. So I like when I ask a question, you're able to answer, try and answer anything. So luminous objects, those producing their own light. We can give an example of the sun. I remember Abdul Karim was able to give us the sun. Another one talked about the electric lamp. The fluorescent tubes, they produce their own lights. The candle will produce its own light. We also have what we call the glowworm. I hope you are putting short notes. The glowworm will produce its own light. And many others, even the television screen. When you look at the screen of a television, the laptop that you are using, the screen of your mobile phone, the iPhone, if you are using the iPhone, is it able to produce its own light? So here are examples of those objects that produce their own light. We have the sun, the stars, the burning candles, wood, charcoal fire. All these produce their own light. Then non-luminous objects, the one that most of us are able to argue out and say, no, it produces its own light, is the moon. The moon does not produce its own light, so it is non-luminous. The moon only reflects light from the sun. The wall of a building, the roof of a building can only reflect light. You, as a human being, you are also non-luminous. You only reflect light from the sun. So all objects that only reflect light, they are known as non-luminous. So a very good, most of them, the examples have been given here. The moon, planets, plants, people, books, walls, clothes, wall charts. I've told you all those are non-luminous. Anyone with a question up to that? So we've talked about the two types of sources of light, luminous and non-luminous. Now, light travels in what we call rays. When we have a source of light, the light energy will move in all directions, and light follows a path. A vehicle will follow a path which we refer to as a road. But for light, we cannot say that this is the road of light. The path followed by light, we refer to it as a ray. So light energy travels along a path which is known as a ray of light. If there are so many paths of light, then we refer to them as rays of light, and together they form what we call a beam of light. So we have rays and we have beams of light. If it's 1, it's a ray of light. So a ray of light is the path along which light energy travels. Then a group of rays is what we refer to as a beam of light. Those are many rays. So of course, therefore, anyone who is making very short notes, you don't write a lot, just short points. Like you have written the meaning of a ray of light, the path which light energy travels along. Then we are talking about a group of rays. We are referring to that as a beam of light. Now, beams of light, we have types of beams of light. Now, if the light rays, so these are the 3 types of beams of light. We have the first one, divergent beam. For example, the rays from a torch, from a bulb, they spread out. They appear to be diverging. So we refer to this as a divergent beam of light. Light rays come from a source and they spread out. The second type of beam, we call it the parallel beam of light. The rays of light are parallel. They don't appear to meet anywhere. This, for example, for the car headlights, most of the time the car headlight can be adjusted so as to be the rays of light to be parallel. So they form a parallel beam of light. And then you can choose to focus light at one particular point using a lens, which we learn in Form 4. When light is converged or appears to meet at a given point, we refer to that as a convergent beam of light. So up to there, please know what's a ray of light. And then a group of rays of light we refer to as a beam. Then we talk about types of beams of light. Divergent beam, the parallel beam, and then the convergent beam. So you can see from the diagram, to diverge is to appear to spread out from a given source. And to converge is to appear to come together. So the diagrams clearly illustrates what we refer to as the 3 types of beams. Yeah, the best way of remembering is just short notes. Short notes, you can even make a diagram, if you have freehand or you have a ruler. That will make you to remember, because what goes through the hand, it goes to the brain and sticks. But if you just maybe sit, then we talk and talk. So you make sure your fingers are very busy as you listen, then you make some short notes. It's very important. Now, apart from talking about luminous and non-luminous objects, we have other objects. I want to talk about opaque objects, translucent, and transparent objects. Now, opaque objects, when you talk about opaqueness, these are objects that do not allow light to pass through them at all. Like if we have Hassan Ahmed standing just in front of light, you'll find that if he's standing next to a wall, we shall see a shadow of Hassan Ahmed cast on the wall. That shows that he is an opaque object. So an opaque object does not allow light to pass through it at all. Examples of opaque objects, we have brick walls, we have metals, we have wood, we have stone, we have human beings, animals, trees, name all of them. As long as when light shines on them, they form shadows, then we refer to them as opaque objects. Now, we have what we call translucent translucent objects. In most cases, when we go to the washroom, most of the modern washrooms, you'll find that they have some special window panes. They have some special glasses placed on the windows. When you are inside the washroom, you can't see outside, but light from outside will be able to go through and you will be able to see the light inside, but you can't see what's outside. So a translucent object will allow light to pass through it, but you cannot see through it. A windscreen of a car is not translucent because when you are sitting in front of the car, you are able to see through, light comes through the windscreen, and you're also able to see through it. So that means it is transparent. Light is passing through, and you can also see through it. But anything that allows light to pass through it, but you cannot see an object on the opposite side of it, then it means it is translucent. If you take a piece of paper, then you smear it with some Vaseline or some oil, that paper in most cases becomes translucent. You are able to see, light is able to pass through that paper, which is oiled, but you cannot see through that paper. You can't see an object on the opposite side. So that means it is translucent. So some of the examples we are seeing here are glass panes used in the toilet and bathroom windows and greased paper. Those are some of the materials which are translucent. Then of course I've talked about transparent. So remember the 5 objects we have talked about: luminous objects, non-luminous objects, opaque objects, translucent objects, and then transparent objects. So those are the types of objects you have to know when it comes to this topic, rectilinear propagation of light. Now, when you talk about rectilinear propagation of light, when you are in primary science, you are being told that light travels at this speed. Then you are being asked to compare the speed of light and the speed of an aeroplane, the speed of light and the speed of sound, that between sound and light, which one travels faster? Both in between sound and light, which one travels faster? Yes, Mohsin Shafi.
Light travels faster than sound.
How can we demonstrate that to show that light travels faster than sound?
For example, the lightning.
Lightning, very good. Any other example?
We hear the light and then after that's when we hear the sound. We see the light and then we hear the sound.
Very good. You see the light, then you hear the sound. Now, is it true that light travels in a straight line? Zamzam?
Yes.
What evidence do we have to show that light travels in a straight line?
Putting the cardboards on us.
Putting the cardboards on a line. Any other evidence to show that light travels in a straight line? Let me look for somebody to help you. Evidence. What evidence do we have to show that light travels? Salma Ali. Is it true that light travels in a straight line? Yes or no, Salma Ali? Or if you're not sure, tell us that you are not sure. Yes? Please, I told you, let's interact, let's talk. Talking is knowing physics. Abdul Basit, does light travel in a straight line?
Yes.
How can you tell that light travels in a straight line?
Formation of shadows.
Formation of shadows. Very good. So, those who came late, we had shared a video to show, to demonstrate an experiment to show that light travels in a straight line. When you are asked in an exam to give evidence that light travels in a straight line, you don't talk about this experiment. This is a simple demonstration. I'm repeating it for 2 minutes. I want you to listen to it for those who came late. This is a simple experiment we can carry out in our laboratory as evidence that light travels in a straight line. So this is a verification. So don't confuse in the exam when they ask for a verification and an evidence. So this experiment is not an evidence. The experiment is a verification. You want to prove that light travels in a straight line. But evidence, it's like what Abdul Basit has told us, formation of shadows. Now, this is the verification to show that light travels in a straight line.
Through a tiny hole in the window, what do you see? Do you see light traveling in a straight line? Hello friends. Today we will perform a very simple experiment to prove that light indeed travels in a straight line. All that you would need to start.
Please listen clearly. It is saying an experiment to prove that light travels in a straight line. We are not talking about evidence that light travels in a straight line. So you must get the clear difference between that. This is an experiment to show that light travels in a straight line. Then we have the other question which I asked. Evidence that light travels in a straight line. This is not evidence. This is an experiment.
The experiment are 3 old CDs. So the CD should be old because during the experiment, they might get scratched. Thread, a candle, and 6 clips. These clips we normally use to dry clothes. So first of all, we will have to make a stand for these CDs. So for that, we will make use of these clips. So hold the CD upright and then fix the clip. Please make sure that the CD remains upright, that is, it should be perpendicular to the plane of the table. So this is ready. In a similar way, we will do it for the other 2 CDs. So now all the 3 CD stands are ready. So what we want to do now is, we want to align these 3 in a straight line. We have to align them in such a way that the holes of the 3 CDs lie in a straight line. So how do we ensure that they are in a straight line? So for that purpose, we will use a thread. So we take this thread and we tie it straight on the table. So you can make use of sellotape to fix it at both ends. So you see, now you have a straight line. So now we'll place the CDs one after another. So now when you place them on the thread, then you know that they are exactly in straight line. Now you take the candle and place it at one end. You can place the candle also on the thread. So now make sure that the tip of the candle and the holes of the CDs, all of these lie in a straight line. So for that, you will have to ensure that the height of the candle and the height of the hole of each of the CDs, they are the same. Now try to observe the flame of the candle from the other side. So your line of sight should be same as this line, the holes on the CDs. And you are able to see the flame right now. Yes? Okay. Now, why do you see this flame? That's because light travels through these holes and reaches your eye. Now let's see what happens if we displace the middle CD slightly. The moment we displace it a bit, what happens? Are you still able to see the flame? No. Why did that happen? That's because the light came here and it got blocked here. Because we have displaced the CD, the hole is not there. So the light is not able to come any further and you are not able to see it. Now, had light the ability to take curved turns, in that case light could have actually taken this turn and then it could have come through this hole and you could have seen it. But since light travels in a straight line, therefore we did not see the flame. So this experiment very clearly proves that light always travels in a straight line.
Very good. And very clear to the point. that this is an experiment to show that light travels in a straight line. So it's not an evidence that light travels on a straight line. It is an experiment to verify. Now, this property of light traveling in a straight line is what is known as rectilinear propagation of light. I repeat, the property of light traveling in a straight line is also known as rectilinear propagation of light. So, in most cases, when they ask you questions to do with from that experiment, what do you conclude? What property has light shown in this experiment? The property shown by light here is the rectilinear propagation of light. In other words, light travels in a straight line. So to just go back to our slide and move on a bit. Okay. Okay. So from the current to on. So this experiment which have just been shown, so light travels in a straight line. The property is known as rectilinear propagation of light. Please remember that. If you are asked, what property does light show when it travels in a straight line? We refer to it as rectilinear propagation of light. So as the topic suggests, that light travels in a straight line. Now we want to move on to what we call shadows. So we are now starting on the evidences to show that light travels in a straight line. The three evidences to show that light travels in a straight line, there are only three evidences to show that light travels in a straight line. I'll want to put them down shortly. So the first evidence is formation of shadows. That's the first evidence. The second evidence, occurrence of eclipses. And the third evidence, as we shall be looking at, is images formed in a pinhole camera. So those are the three evidences that we want to look at. So the previous one was an experiment to show that light travels in a straight line. But now, these are the three clear evidences that show that light travels in a straight line. And the first evidence is the formation of shadows. Light cannot bend around an opaque object to illuminate the whole of it all round. When we have eclipses occurring, that's evidence that light travels in a straight line, because when an eclipse occurs, we have umbra and penumbra, as we shall look into that. Then we shall also look at a pinhole camera. So these three are the ones that show the evidence of occurrence of eclipses. So I want to share another short clip about a shadow.
Umbra and penumbra.
So,
A point source produces a single well-defined shadow, while a penumbra
I'm sharing you. Okay.
umbra and penumbra. A point source produces a single well-defined shadow, while a bigger source of light produces shadows like umbra and penumbra. Let us carry out an activity to understand umbra and penumbra. Place a ball fixed on a point source.
Good. Get the point clear here that we have a point source of light and we have a bigger source of light. So they are giving us two sizes of light. One is a point source. That means a small source of light, and we have a bigger source of light. So look at how they are going to form the shadows.
Produces a single well-defined shadow, while a bigger source of light produces shadows like umbra and penumbra. Let us carry out an activity to understand umbra and penumbra. Place a ball fixed on a stand and a screen in front of it such that the screen is bigger than the height of the ball. Now, light a torch from the other side of the ball and see its shadow formed on the screen. Umbra is the part which is in complete darkness and receives no light from the torch, while penumbra is the part which is in partial darkness and
Good. Mohsin Shafi, can you name for us two types of shadows?
Of shadows.
Name
Umbra
for
and
us two-
penumbra.
Umbra and
Penumbra.
Very good. Zamzam, name for us two types of shadows.
Umbra and penumbra.
Very good. I like the way you are all paying
some
attention.
light from the torch.
Okay.
Bring
Just
the ball
slightly
close
back.
complete dot,
Slightly there.
which is in
Okay.
complete darkness and receives no light from the torch, while penumbra is the part which is in partial darkness and receives some light from the torch. Bring the ball closer to the screen. What do you observe? Yes, you are right. As we move the ball near to the screen, the umbra reduces, whereas the penumbra increases.
Good. Now, if you are asked to give the difference between umbra and penumbra, Omar Sayan, what is the difference between the two shadows?
One is impartially dark, and the other one is partially dark.
One is total darkness, another one partial darkness.
Darkness.
So which one is for partial darkness?
That is umbra.
Which one is for partial darkness?
Umbra.
Umbra is partial darkness. And which one is for total?
Darkness. Yes.
Please, I'm just, I'm interested in that. I just want to play it back and Omar Sayan,
Umbra and penumbra,
I want you to
while
see.
penumbra is the part which is in darkness and receives no
There, I'm playing back
Umbra.
there. Omar Sayan, please pay attention there. The two types of shadows and the clear difference between them. Which one is for total darkness and which one is for partial darkness? Remember, the one for total darkness does not receive light at all. So umbra, that shadow umbra is formed because that part of the opaque object, that object, the ball, there is that part that does not receive light at all. And therefore, the shadow formed will be the umbra. Umbra or umbra is the a shadow for total darkness. Omar Zoyan, please, I want you to get that difference. And the others, maybe who are confused. And then we have penumbra or penumbra. See, the one outside there, that is the shadow of partial darkness. That means this object at that point on the sides has received some light. That's why the shadow is not totally dark. Get that clearly there.
the part which is in complete darkness and receives no light from the torch, while penumbra is the part which is in partial darkness and receives some light from.
So total darkness does not receive light at all. Partial darkness receives some light. So that is the first evidence that light travels in a straight line. The shadow is formed because light from the source, that's the torch, does not go around to illuminate the whole ball. So that's why the shadow is formed. Now, what other question can we get from here? Let's take, for example, you have an opaque object somewhere in a room or on the road. Then you observe and you see 3 different shadows. I want to repeat that question. We are talking about the shadow as an evidence that light travels in a straight line. A shadow is formed as a result of an opaque object standing in the path of light. So, supposing we have an object, maybe you're walking in the streets of Nairobi or anywhere, any street, then we have those street lights. Then you look at a given object, like maybe a stand of one of the street lights. Then you see there are 3 different shadows. What will you say about, what could be the source of those 3 shadows? The question is open for anyone to try. You just unmute yourself, then you will come on the screen, you try to answer.
Mr.
Anyone?
Sifuna, one of the students is asking, requesting that you repeat the question.
I repeat the question, huh? Okay. Now, the question I was asking is this. I hope you are all seeing this phone. I'm holding a phone. So as I hold this phone, you find that when I check around here, it's possible I can be able to see 3 different shadows. What could be the reason as to why I'm seeing the 3 shadows? One thing I want you to know is because one of the shadows could be penumbra. Maybe there is a large source of light in the surrounding. So I'll see a shadow of total darkness and another shadow of partial darkness. The third shadow, or if we have a third shadow, could be possible that for the 3 shadows to be there are 3 different sources of light and in different directions. So when a source of light is on my right hand, the shadow will be formed on the left. If we have another source of light on the left, the shadow will be formed on the right. And if we have another source of light in front, the shadow will be formed at the back. So that's how to reason out. We may have many number of shadows, condition being if we have many sources of light. If not, more than one shadow, it could also mean we have a large source of light. That means we shall have the umbra and the penumbra. But if we have an object and there is only one shadow formed, then you are asked, why do we have only one shadow? What will you give us the answer? Okay, I'll repeat. So the first question I've tried to explain why we may have many shadows, because we may have many sources of light and a large source of light. So my other question I'm asking, why is it that when we have an opaque object, what is it that will lead to us seeing only one shadow? Yeah, I'll choose somebody just to try. Mukhtar. Yes.
Because there is a use of only one source of light.
Yeah, very good. That's a good try. Only one source of light. Supposing the source of light was a large source of light, shall we see one shadow?
No,
How many shall we see?
more than one shadow.
In most cases, we talk of only two shadows. So my question was, I'm still talking to Mukhtar, so I'm still talking with you as others are listening. Under what condition shall we only have one shadow being formed? Try. That question I've asked so that all of us, let's remember that we might have two types of sources of light. A small source of light, which you call a point source of light, and a bigger source of light. If we have a small source of light, in most cases, it will only give one type of shadow, which we call the umbra. So when you see one shadow of total darkness, then that means the source of light is a small source of light. That is the one which will give only one shadow, the umbra. But if the source of light is bigger, it will give umbra and penumbra. If the sources of light are many, then we experience many shadows. So get that point clearly, that to have umbra only, the source of light must be a point source or a small source of light. But for us to have more than one type of shadow, then one, the source of light must be bigger. Two, we may have many sources of light. Anyone with a question, you can ask. It's good. It seems nobody has a question. So we are almost moving on to the almost last evidence. The last evidence, in 5 minutes time, we shall be stopping. I want us to look at the pinhole camera.
Have you ever seen light rays coming through the holes of a damaged roof?
So
Will you surprise? Have you ever seen?
Just sharing with that in 2 minutes time, then we stop there.
Light rays coming through the holes of a damaged roof? Will you surprised to know, as you can see, that the light rays from such holes produce images of the sun when they fall on the ground? Why? Because these irregular shaped holes in the roof act as pinhole cameras. Now, what are pinhole cameras? Let's first construct one pinhole camera and then let's try to understand the principle. Now, by definition, a pinhole camera is a simple optical device that forms an image without using a lens or a mirror. That's surprising. Now, let's join two hollow cylindrical boxes of different diameters in such a way that one box can just slide within the other. Now, what do? We make a small hole in the larger cylinder there, and also make two holes in the smaller cylinder, the one inside. Fine? But there is one care you need to take. The inner hole has to be rectangular and the outer hole has to be circular. We now fix a translucent paper, say a tracing paper, on the rectangular hole because that's going to act as a screen. Now, very importantly, these two cylinders must be enclosed so that you can prevent light from entering the larger cylinder. That will mess up our image. Now, use this pinhole camera and try looking at a tree. Surprise! A clear image of this tree can be obtained on the screen if you slide the smaller cylinder bracket forward. Now, how exactly did it happen? Let's look at this diagram. The tree is, say, MN. M is the topmost point, N is the bottommost point. The light rays coming from the bottom of the tree, that is N, they pass through the small hole and strike the screen at the top of the axis, N dash. Can you see that? And the light rays coming from the top of the tree, that is M, strike at the bottom of the axis, that is M dash. Now, what happens as a result?
You can see that is evidence that light travels in a straight line. We are not seeing the rays from M. When they go through the hole, they don't go to form at the top. The rays from the top, they go to the bottom, and the rays from the bottom, they go to the top. That means this is evidence that light travels in a straight line. So a pinhole camera is an evidence to show us that light travels in a straight line. Rays do not bend, they go straight, and you see the image, how it's formed. Yeah. Now, Omar, how do you see that image? You can see this image here. Can you describe it in relation to the object? Yes, try. We are not hearing you. Check your sound system, Omar. How do you compare this? You see the top of this tree here. Then you see where the top has gone. It's down here. And the bottom has gone up here. So what do we say about the image? Whether can you assist Omar? How do you describe this image? Yeah.
Inverted.
It is inverted. Very good. So class, I want you to remember that. We have shown the formation of shadows to show evidence that light travels in a straight line. We had just begun on the pinhole camera to show also that it's evidence that light travels in a straight line. And we have, from the start, looked at various concepts. So just to share you so that you have an overview as we end our lesson for today. Please, we have shown an experiment to show that light travels in a straight line using the CDs. I know most schools, they use cardboards, but you see CDs can work very well as evidence, as an experiment to show that light travels in a straight line. Then we have talked about 5 different objects. We have talked about luminous objects, non-luminous objects, opaque objects, transparent objects, translucent objects. We have talked about beams of light, which were 3 of them. And we had just started on the evidences to show that light travels in a straight line. So in our next lesson, we are going to finish with the pinhole camera. Then we look at the formation of eclipses. And then we go to reflection of light as we continue with the topic. Otherwise, up to that, I just want to encourage you that when we have the next lesson, please let's interact. Physics involves us talking. Let's talk a lot. Let's ask questions. Let's answer questions. Otherwise, I love this class. It's a good class. And I know I've known Abdul Mukhtar, I've known Rueda, I've known Hassan Ahmed, Abdul Karim Ahmed, Zamzam, Omar Soyan, Salma Ali, then Abdul Basit. Those are the people I've known today. There is also Mohsin. Sorry. Mohsin. Yeah. I want to wish you a nice weekend. I'm seeing your director there. I really appreciate for this session. Otherwise, for today, I wish to end there and say bye-bye to you all.